Hello everyone, so here we are back. This is the fourth video after you've watched the two Brendan Fultz videos. And instead of going into PowerPoint, which would only have been a couple of slides anyway, I'm going to go directly into the script. So I have created a MultiReg.r script, which is posted to the Canvas course. And I've also posted the Toyota Corolla dataset. And so this script is going to show you how to set up a multiple linear regression. It's also going to show you how to set up a couple cool functions, and these are actually covered in the textbook, how to set up a training set and a validation set. So the Toyota Corolla file it's not huge, but it has 39 variables, most of which we don't really care about because we're only going to try to use a couple of those variables to predict the actual prices of the car. So we're going to dump most of them and just use the ones that we care about. We're also going to take the file and we're going to divide it into two sections, a training section, which will be 40% of our records. I'm sorry, 60% of our records, and a validation section, which will be 40% of our records. And I'll show you the commands that we use to do that. What I'm going to do is I'm going to walk you through setting up a multiple linear regression. We're going to use three fields. We're going to check those three fields first, visually with plots, and then we're going to calculate correlations. And then just like Brendan Fultz did in his videos, we're going to check the independent variables, the three independent variables against each other to see if there's any collinearity that we might want to eliminate. Once we've got that all worked out, we're going to go ahead and run a multiple linear regression, and then we're going to check to see how accurate it is, how close we came to the actual price, and how much error we have. That's where I step out, and then you step in, and you're going to do the same thing, only you're going to do it this time on the validation set. And there's a couple of things, actually 6 things, I want you to turn in. At the end of the script, I go into detail about what those are, and they're also listed out in another part of the Canvas course in Module 6. Okay, so let's start working through the script. So I wrote the script. It builds a multiple linear model to predict car prices. Okay, so the first thing we're going to do is we're going to read in the data file. So car.df is going to be set equal to the results of read CSV, and the file name is toyotacorolla.csv. Let's go ahead and run through those first few commands. File is in, okay, but the file's about 14 or 1500 rows, and we're just trying to build a model, so we don't need a lot of extraneous stuff. So what we're going to do is we're just going to settle for the first 1000 rows. So we're going to set car.df, the data frame that we just created, we're going to set that equal to the first basically 1000 rows and all columns. We still have all 39 columns. We'll deal with that later. So let's go ahead and run through that. Okay, and now we have a file that just has 1000 rows. Okay. Now we're going to narrow down the possible columns, and what we're going to do is we're going to build an index and use that index to create our training set and our validation set. So it just so happens that we know that variables, I should say, in columns 3, 4, 7, 8, 9, 10, 12, 13, 14, 17, and 18 are ones that could possibly be useful in a multiple linear regression exercise to help us determine the price of the car. So those are the ones we're actually going to get. So in order to do this, we're just going to set basically a vector, and the selected.variables is going to be a vector that's going to contain those numbers. So we'll just set that up for now and then set it aside. Okay, that's done. Okay, now we're actually going to build those two training sets. Remember I said that the training set is the first one. It is 600 rows, or 60% of our data file. And we're going to basically pick those 600 rows at random. And then when we also pick those rows, we're going to create the data file using just the columns that are numbered in that vector that I set up. So let's go ahead and run through some of that. Okay, we're going to build our partitions. This set seed 1 actually starts our randomizer at the number 1 so that it doesn't cause us problems. We'll build the partitions. 600 for training, 400 for validation. Okay, the training.index is set, and that training.index is set to take a sample, and it's going to be build a vector anywhere from 1 to 1000. So what that is basically doing is between the numbers 1 and 1000, it is selecting a random sample of 600 of those numbers. Okay, and that's creating an index because that random 600 numbers will be used to identify the rows that we're going to pull out that become the training data set. So that becomes just our vector, and it's specified at 600. So between 1 and 1,000, pick 600 random numbers, dump that into train.index. Okay, now we're going to actually build our sets. So train.dataframe, our training data frame, is going to be set to car.df, and we're going to specify for rows the 600 random numbers in train.index. And for columns, it's going to be selected var, these guys up here that we picked. And that will set us up with a file that has 600 rows, 600 random rows with just those variables. Now we want to pick up our validation set. And our validation set is going to be set up pretty much the same way, except for now what we're going to say is in the validation set, put all the stuff from car.df that is not in the training index. So this is the 400 that didn't make it, didn't make the cut when we did the random sample. So, and then also the same selected variables. Once we do that, we have our 2 data files set up. So let's go ahead and run through that. All good. Okay. Now we're going to have to try to figure out, all right, what are we going to look at in terms of variables that could potentially lead toward the prediction of the price variable. So we've got a couple of them that we look through. If you actually do a view of the file, you'll see that the file contains those variables that we selected in that vector. But the problem is that some of those variables, even some of those, aren't very good. They aren't going to be very useful. So we could go ahead and create another vector, another subset of the subset of fields that we have, that are numeric fields that could potentially be used as ones that would help us predict the price. So what I have done is I've created a variable, that's my correlation columns, and I'm going to set that equal to the vector that contains numerical values, of which there are, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So 8 numeric values that could potentially be useful. And there are things like age and kilometers and weight and all kinds of stuff like that that could potentially help us predict price. So we'll just set that vector equal to those columns. And then what I'm going to do is I'm going to come down below and I'm going to say, okay, I want to run a correlation. And I want you to correlate in my training data set all rows and those core calls, that vector that I set, those 8 columns. And what that will do is that will run a multi-dimensional correlation coefficient between each variable and every other one of the 7 variables that are in the list. That becomes really useful because it lets us see what the correlations look like. So let's go ahead and run that. I've set my vector, and now I'm going to run this correlation. And it gives me, and really the first one, because price is what we're trying to figure out. We're trying to figure out what's correlated with price. Well, price is very correlated with price because it is itself, so it's a correlation of 1.0. But when I look down the other variables, and these are the remaining 7 variables, I can look at the correlations and see which ones have high correlations and which ones have kind of low correlations. So now remember that a correlation, if it's 1, it's high. If it's -1, it's high. It's just in the opposite direction. So something that looks like this with a -0.86, that's actually a relatively high correlation. And it makes sense because the age of the car should be relatively tied to the price of the car, but it would be in opposite directions. The higher the age, the lower the price, and vice versa, which is why you have a negative correlation there. Same kind of thing works for the kilometers. The kilometers is pretty tightly correlated with the price. It's just in an opposite direction. The higher the number of kilometers, the lower the price. So that one looks pretty good too. There's horsepower, cubic centimeters, doors, and quarterly tax. None of those look really very good. We got a 0.3, 0.13, 0.18, 0.22. Not probably really tied to the price of the car. So it's probably not going to be a very good predictor for us. The last one, however, is weight. And that one says that it's got a 0.586 correlation, and that's positive correlation. So that means the heavier the car, the higher the price. So it looks like we've identified 3 possible variables that could be used to help us build a multiple variable regression. So let's take a look at those. We'll come back over here, and we're selecting age. That's actually age 0804. Kilometer and weight as 3 potential fields to build our model. And now we'll run plots to see how well each one matches the price variable. And we are also checking each dependent variable against the dependent variable. So this is the first step that Brandon Fultz talks about. So let's go ahead and run through that. All right, plot price against age. Well, that looks pretty good. Looks like a pretty tight correlation. We expected to see that with a 0.86, and it's negative because it's going in the opposite direction. Okay, it's going from the upper left to the lower right. So that looks like a really good candidate. Let's run the next one. That looks similar. Remember, this one is kilometers and it has a lower correlation. It looks pretty good, right? So I think we can probably keep that one for now. And then the next one, that one has a positive correlation. It looks a little bit like the one we just looked at, but it's still pretty good. It's still pretty tight. So we'll go hang on to all three of those variables. Nothing looks really goofy. The reality is that we looked at the correlations before, so we knew what we were going to get. So this is kind of an extraneous step, but still, it's worthwhile. All right. Now we're going to plot the independent variables against each other. Remember, this is to check for collinearity. So we really want to eliminate any pairs of variables, or pare it down to just one single variable, where the two are tightly correlated. And if they're tightly correlated, what that's going to cause is collinearity. It can throw your model off. It's really unnecessary to have the two variables if they're so tightly correlated that you can really represent the behavior with just one of those variables. So we're going to take a look. And we're going to use plots. Okay, so the first one we're going to plot is going to be the age against the kilometers. What does that look like? That looks okay. There's a lot of scatter, so there's a lot of, if there was a linear regression line, there's a lot of scatter around that line. There's a lot of variability in this. So we'll say that that's, some might want to throw that out, but we're going to keep it. Okay, we're going to move on to the next one. That one looks like there's not a real pattern there at all, but that's the comparison of age versus weight. So that one doesn't look like we're in too much danger. And then if we go on to the next one, that one looks like there's not a lot of danger there either. Okay, so it looks like we could keep all three of our variables. The only one that was really kind of a tough one was the first one when we compared the age versus the kilometers. And that one might be one that we were a little suspect of. But anyway, we'll just imagine that they were not correlated at all. A lot of them didn't look like they were that much, so we're going to keep them. The next thing we're going to do is something we've kind of already done, but I'll go through it anyway, and this is to run correlations. And the first thing we're going to correlate is we're going to actually check the price variable against the three independent variables. Price, of course, is your dependent variable, and we're going to check it one by one against each of the three independent variables just to see what the correlations are. Now again, we already did this over here when we ran the big mass correlation, so we don't necessarily have to do this step, and you're not going to get anything out of this that you don't already know. There's the first one. Remember, it was a 0.869 negative correlation. There's the second one. It had a 0.58 correlation. That was negative as well. And the third one has a 0.586 correlation, but that one's in the positive. Again, we already knew that, but if we hadn't run that big correlation table up above, you could do these individually. What we don't know, though, is how the correlations look for the independent variables when we compare them against each other. So let's go ahead and run that. The first one that we're looking at is age versus kilometers. And the correlation, this is the one visually that looked like it might be sort of correlated, but it's kind of a moderate correlation. So it's 0.544. It's a positive moderate correlation. We can make a judgment call and say, well, I don't think there's going to be that much collinearity, or there might be power in actually keeping both of those variables. So we're going to keep them both. So that one's okay. The next one is negative 0.48, or basically negative 0.5. Again, a moderate correlation. We'll make the same judgment call on that one and keep that one. The last one is basically no correlation at all. It's basically 0.08. So that's definitely one we could keep. Weight really has no real relationship with the kilometers. And so we're definitely going to hang on to that one. Okay, so each of those independent variables had a reasonably good correlation, and that's why we selected it, to the dependent variable of price. But when we look at them compared to each other, there's not a lot of overlap. There's some overlap, but not a lot of overlap. So we're just going to assume that all three of them are going to be good to keep. So the next thing we're going to do is we are going to run our model. So we've got these variables, we've checked them out, and how do we build our model? So we're going to set up a variable called cars.model, and we're going to set that equal to the results of the linear modeling function, where we put in price and we compare it to all three of our variables. The first one is age 0804. The second one, which we indicate with a plus sign, is kilometer. And the third one, which we also indicate with a plus sign, is weight. Each time you want to add a variable to your linear regression comparison, you just use a plus sign and add that variable in. We then, of course, have to specify that the data that we're using is going to be our training data set. So that's the 600 records that we set aside to actually build our model. So let's go ahead and run that. I'll skip through those comments and we'll come down here and run that. And it's done, okay? So we want to be able to display that. One thing that we're going to do first, though, is we're going to set an option, and that option is going to be basically this command is to set me, show me the number of digits after the decimal and limit that. Otherwise, I might get scientific notation, and that's not going to be very useful. So this basically prevents that from happening. And now I can run summary. Summary is the command I want to use for cars not model because summary will give me a bunch more information. And when I do that, I'm going to get a ton of information, much of which I don't really need. So it gives me information about residuals and the range of residuals. It gives me down here different values. It gives me the p-value of each of these so you can see what the p-values are. But really, there's just a couple things in this that I'm really interested in. The first thing I'm interested in is the intercept. Remember I said that you will get one intercept and you'll get multiple coefficients, one for each of your independent variables. So here's your intercept in this 2095.185143. It has a standard error, it has t-value. Fine, we really care about the intercept. Okay. And there are three variables, age, 0804, kilometer, and weight. And each one of those has a coefficient. So the coefficient here, negative 135.626079, is what we're going to use when we build our model. And we'll use this coefficient for kilometer and this coefficient for weight. Okay. So essentially what we're going to do is we're going to take this value, this intercept value, and we are going to add it for every one of our 600 records. We are going to add it to the age, kilometer, and weight multiplied by their coefficients. And that will give us a estimated price or a predicted price for every one of our 600 records. Let's take a look at how that would look in the script. Scroll down a bit. All right, just like I said, we have a coefficient and a slope for each variable, or coefficient for each variable. And we're going to go ahead and set up our equation. So to do that, I'm going to actually specify a new variable. That new variable is predicted value, and predicted value is a variable in train.df. It's not a column that's currently there. That's one thing that's beautiful about R, is it's so easy to create a new column. You just create a new column and tell it what it is. So train.df is going to be set equal to my intercept, which is my value over here, plus the variable train df.age 0804 times its coefficient, which is specified over here, plus the variable train.df $kilometer times its coefficient, and lastly, we'll have weight times its coefficient. Okay, so you see how those are set off in parens, just to respect order of operations. Each one of those is set off in parens. We're just multiplying that record, the variable for that record, by its coefficient and adding it to the intercept. Okay, it'll do this 600 times. It'll run through all 600 records, and for record number 1, it's going to take the first age, the first kilometer measurement, the first weight measurement, multiply it by the coefficients, add it to the intercept, and drop it into this new column, predicted value, in slot 1, row 1, because it's pulled those variables from the first row. So it'll go ahead and do that for us and set up that column. It'll complete that column all at once. So it's pretty fast. Done. Okay. So how does it look? Well, let's take a look at it. When I look at it, I don't really want to look at all the extraneous columns. I do want to look at all 600 columns, but I only want to look at the actual price and my predicted price. So I can use the square brackets to limit the number of columns that I see. Remember, the empty space says I want to look at all rows, comma, but this is my vector that says limit me to just column 1 and column 12. And so it will do that for me. And now I can look at price, and I can look at predictive value, and I can see how close or how far I am when price is compared to predictive value. There's a couple tools, a couple ways that we can use to look at this to see how close we were. But before we do that, let's take a look at the comparisons more kind of at a larger level. The row names were the random numbers that were generated between 1 and 1,000 that we use as an index to actually pull those values, and it's just kind of coming along in the data frame. So this is really column 1 and column 12. All right. We have error, as you could see. When we looked at our view of our data file, we could see that there was a difference between actual price and predictive price. So we're going to go ahead and calculate the error for each row by subtracting price from predicted value. And the way we do that is we create yet another column in our data file. This is going to be train.df $error. I'll just call it error, right? And that is set equal to the predicted value minus the price. Now, and that will give us basic what the difference is. It doesn't matter which way we just subtract it. So let's go ahead and do that. And we can view the results. Okay. Again, we have price, we have predictive value, we have error. It's really important to note that your errors, some of them are positive and some of them are negative. And we want to start looking at error more and more because error is really an indicator of just how good our model is. The smaller the error, the more accurate our model, obviously. One thing to remember about error, and this is something we'll talk about next week when we do a short little presentation about errors, is that if you're dealing with a regression, building a regression model, chances are, the way that this works out, you will have as many errors above your line as you would have below your line. So in a true, really accurate, single regression model, your errors have the real potential of canceling each other out because you have as many points above as below. Or you're going to get a really small error if you just sum them up. That's kind of the problem that we see here when we do this. And we'll talk more about that next week, but just note that there's as many negatives as positives. Okay. All right, I want to look at one more thing here, and that is I want to see two things actually. I want to see a little bit more about error. I want to see, first of all, what is the mean error? So the mean error, let's go ahead and run that real quick. And that's just the average of the 600 error measurements that are in my training data set. And it comes out pretty small. And the reason why it comes out pretty small is because, remember, when you're doing an average, what's the first thing you're doing? You're adding them all up. Well, if you have as many negatives as positives, you're going to get a pretty small value when you actually add them all up. Then you have to divide it by 600. So that's a pretty small value. Not terribly useful, but it does give you some sort of an idea of what your sort of a single metric for your error. Next week we'll look at ways to do this to get around the problem of values canceling each other out. Another way we could look at this is we could just plot the two values that we got. We have price and we have predicted value. Okay, when we compare price to predicted value, what does it look like? How does it look? Let's do it visually first. And it looks pretty good. So we have a pretty tight what looks to be a pretty tight correlation that follows a nice diagonal line, and it looks like it's there's not that much scatter around, the diagonal line. Everything looks pretty good there. Let's just take it one step further and do a correlation. What would we get if we ran a correlation between those two variables to see how tight our model is? We get a correlation of 0.90, basically 0.91. Not bad. That's pretty good, actually. So we have created a model now. We've used 3 variables. We've created the model. We've tested our model. We've calculated the error. We've come up with a mean error. We've looked at it using the plot command, looked at our predicted value versus our actual value, and we've looked at the correlation between the two. So that's as far as I'm going to take you. Now, you're going to have to do the rest. I want you to do basically 2 classes of things. The first thing I want you to do is I want you to run through the training data frame, and I want you to drop one of the variables. So the one you're going to drop is weight. So instead of this being a 3 variable predictive model, it's going to become a 2 variable predictive model. You're going to have to drop weight. You're going to have to run the lm command on just the 2 variables, and you're going to have to come up with what the coefficients and intercept are. Then you're going to have to rebuild your or calculate a new predicted value. You'll still have your old predicted value in your data frame unless you start over, but you can call it predicted value 2 or whatever you want to call it, and come up with what the predicted value and the error is going to be. Okay, so actually I give you already variable names. Adjusted price. Okay, so adjusted price will be your predicted value for when you drop the weight variable. Adjusted error is going to be your error for when you drop the weight variable, and you'll calculate the mean of adjusted error and turn that in. Okay. Now you're going to have to go back to your original model, where you had the three variables. And remember, we've got a training set. We also have a valid set, or a validation set. We haven't done nothing with a validation set. So what I want you to do is I want you to run the triple variable model against the validation set, and I want you to do some comparison. I want to see what the error is. I want to see how it looks in the validation set, because really that's what a validation set is for. So there will be 6 things you turn into me. They're going to be the average error in train.df with all 3 variables in the model. I already gave you that one. That one's already in this video. You'll see it. Then run the intercept and coefficients when you drop weight out of the model. I want you to put that into a Word doc. You can drop all these things into a Word document and just turn them in as a single Word doc. And then give me the average error in train.df with just age 04 and 0804 and kilometer. Again, once you've dropped weight, give me the average error. So I want 3 things from you on the first one. Give me the average error, then drop weight, give me the intercept and coefficients, and give me the average error. Okay, then you're going to go back to your 3 model, or 3 variable model, and you're going to do these things using valid.df. So run the 3 variable model against valid.df, calculate predictive value, which actually I called adjusted value, and error, which I actually called adjusted error, in valid.df. Give me the average error. Give me a plot of the price against the predicted value in valid.df, and the correlation of price and predictive value in the valid.df. Again, you're going to have to come up with your own variable names because you don't want to mess up and confuse it with the first one. So the variables you use, actually, it doesn't really matter. I think I said that you're going to use the adjusted, but that was actually when you dropped the weight one and you're still working in the training set. When you get to the validation set, you don't have those variables yet, so you can call them whatever you want. But anyway, I do want to see the comparison of the plot of the 2 prices, the price actual price value and the predicted price value, and then the correlation of those, just to see if you can give me some sort of an indication of in training. We saw in training that the plot looked really good, and we saw that the correlation was 0.91. So what is it in validation? Is it similar? Is it close? Or is it way off? You tell me. That goes into your Word doc as well, and you tell me what your results are. Okay? If you have any questions or concerns, don't hesitate to contact me.